Yes, students. So let's look at question 3. We are supposed to show that the area expansivity beta of a substance is related to its linear expansivity by the expression beta equals 2 alpha. We are already conversant with this equation and we want to show that, right? So how do we show this? So we are on question 3. Question 3. So we know that area expansivity mathematically, how is it given by? It's given by change in area over original area times change in temperature, all right? So where we know that AI is the original, or we say initial area, delta theta is change, to make things simpler, temperature change. Okay, so let's call this equation 1. Okay, so from 1 we can say that beta is A2 minus A, let me use I and F, okay, all right? A final minus A initial over AI times, can I say that? Where AF is the final area, because we are saying that change in area, if there is change in area, when we hit the metal and it expands, then the change in area will be the final area minus the initial area. Okay, so from this, when we make AF the subject, as we have known already, we know that we will get AI 1 plus beta delta theta. We know this equation already. Let us call this equation 2. All right. So now, when we talk about area has to do with the length and the breadth of the given solid, right? So how can we find AF? We can say that, let's say when the body is heated to get a final area, then we can say AF, we can call AF as, assuming, so let me write this. So assuming, okay, the solid is rectangular. So if the solid is rectangular, then what can we say here? Then we can write that AF will give us LF, length times WF, right? Length times width. So let me call this equation 3. Okay, yes. And applying from linear expansivity, okay, from linear expansivity, we know that the definition of linear expansivity, we call it alpha. We know that alpha is what? LF minus LI, or out of LI times change in what? Temperature. Okay, so from this we saw that LF was what? LI 1 plus alpha delta theta. Okay, we can write that the width still has to do with linear, so we can write this in terms of width as WF will be what? WI 1 plus alpha change in what? Temperature. Is that not it? So let me call this equation 4 and let me call this equation 5. Okay, so now let us put, if we are substituting 4 and 5 into equation 3. Okay, let's substitute equation 4 and 5 into equation 3. Then eventually, what are we going to get our equation to be? Please, just a minute. Let me find a new board so that we can continue nicely. So we can now see that, okay, if we are putting 4 and 5 into equation 3, then this is what I'm going to get. You get, let me write it here before I get the new. Okay, AF equals, so AF equals our LI, LF is what? Is LI, okay, 1 plus alpha delta theta. This is LI, this LF times what? WF is also giving us WI 1 plus alpha delta theta. Now let's try and beautify the equation. If we are beautifying this equation, then we can say Li times Wi, alright, times 1 plus alpha delta theta all squared, alright? Is that not it? So when we simplify this, we know from expansion, now when we have from basic mathematics, then from binomial expansion becomes 2xy plus y squared. Okay, so I'm applying that status here and I'm going to get Li times Wi times what? This will give me 1 squared, which is 1, plus 2 times 1. Okay, let me take my time and break it down. So 1 squared plus 2 times 1 times alpha delta theta plus alpha delta theta all squared, right? So that is what I'll get. Let me put this in squared bracket to differentiate this. So we get something like this, right? So this one will give us this. So when we break it further, then we are going to get Li Wi times what? 1 plus 2 alpha delta theta plus alpha squared delta theta. I hope we get something like this. But we know that, you see, in solace, alpha is usually small, the linear expansivity. And when, so that means that when you square small values, it will be approaching 0. For example, if you have 0.01, square it and let's see. The more you square small numbers, the smaller it becomes. Okay? Yes. So because the normally linear expansivities are small values, this is going to give us something like this. So it's becoming smaller and smaller. So usually linear expansivity, here we are talking about solids, very small. So if it is very small, then we can say that our alpha squared will also be small and it will be approaching 0. Right? So we are using the word approximately equal. Approximately, so it will be approximately 0. This is not equal to sign, it's approximately. So it's approximately 0. And if it's approximately 0, then what it means is that this part goes to 0. All right, and if that part goes to 0, what is our equation going to be? Our equation is going to be AF equals Li times Wi times what? 1 plus 2 alpha delta theta. Is that not it? Great. Sorry. So we get something like this. And we know that L times I, Li times Wi, we can represent it with AI, okay? AI times what? 1 plus 2 alpha, where AI, we know AI already. I have defined it already. So, let's call this equation 6. Now, look at equation 6 carefully. Equation 6 is expressed in terms of AF. Now, let's check equation 2. Compare equation 2 and equation 6. What can you say about the 2? Look at equation 6, right? And look at equation 2. Are they not AF? They are all AF, right? So equation 6 is equal to equation 2, right? So equation 6 is equal to equation 2, or in other words, we can say that equation 2 is equal to equation what? 6, right? Because they are all calculating AFs. Look at this. Okay, and look at this. They are equal, right? So if I equate, when we equate them, then what are we going to get? This is going to be our equation. So we will get AI, okay, 1 plus beta delta theta. That is for equation 2. And equation 6 gave us AI times what? 1 plus 2 alpha delta theta. That's what we are getting. Is that not it? And when we divide through by A, when we divide through by AI, okay, you get 1 plus, the AIs will go, you get 1 plus beta delta theta equals what? 1 plus 2 alpha delta theta. Then, when we subtract 1 on both sides, the 1, 2 will go. We'll be left with beta delta theta is equal to 2 alpha delta theta. And when we divide through by delta theta, we will be left with beta equals 2 alpha. So we have shown it. So as required. That is all. So that is a nice way of proving that equation. Great. This was the question. We started from the definition of area expansivity. We made AF the subject. We put it down. and we are taking it to be a rectangular solid, then the AF will be this. We know that linear expansivity is given by this. We write an expression for LF and WF. We put them in the AF equation. We simplify them. We are going to get this. And when we got this, we saw that 2 and 6 are the same. When you check them, this is equation 2 and this is equation 6. So when we equate them, what are we going to get? We equated the 2, we had this. We simplified it and we have gotten our proof. So that